Hello everyone, I'm Zhou Ye, a PhD student in UC Berkeley. Today, I'm going to present our work, Specular, towards secure, trust-minimized, optimistic blockchain execution. This is a joint work with Ujjwal Misra, Jia Junchen, Wenyang Zhou, and Dang Song. First, a brief introduction to the blockchain as a view of world computer. The user Alice will send her transaction input to the blockchain network. Each blockchain node in the network will execute the input based on the blockchain rule and the virtual machine and produce its own output. Then the node will run a consensus algorithm together to generate the correct output in a decentralized way. However, it is expensive to execute transactions in current public blockchain model. Take Ethereum as an example. There are around 7,000 blockchain nodes scattered around the world, and transactions cost tens of dollars during the high demand period. Therefore, blockchain needs scaling solutions. Optimistic rollups are one of the promising solutions. We use Ethereum here as an example since it is the most popular blockchain with programming ability. In optimistic rollup, Alice will send her inputs as usual to the blockchain network. However, instead of executing by the blockchain nodes, the off-chain executor Bob will retrieve the input from the blockchain, execute it off-chain, and send the output back to the blockchain. In this scheme, the user only needs to pay the cost of storing the input on-chain, but not the cost of execution. However, Bob may be malicious, and his output could be incorrect. To maintain integrity, optimistic rollups introduce the challenge mechanism. Any other off-chain executor call can produce the output on their own and challenge Bob if they find it does not match. The fraud-proof system is where the challenge gets resolved. A special smart contract called on-chain referee will judge either Bob or Carl is lying about the output. A simple implementation of the on-chain referee will be it executes the input on-chain directly and compare it with Bob's and Carl's output. However, directly executing the input on-chain is too expensive. Interactive fraud proof is a common way to reduce the cost of challenge resolution. First, it decomposes the EVM execution into steps according to a certain execution semantics. Then Bob and Carl will run an interactive protocol to narrow down the dispute into a single step. Therefore, instead of the entire EVM execution, the on-chain referee only needs to emulate the specific step of the dispute to decide who lied about the output. Now, the question is, what execution semantics should be used to decompose the execution into steps? State-of-the-art optimistic rollups use an approach called compilation-based IFPs. They take an existing EVM implementation, like Go Ethereum, and compile it into a binary of a reduced instruction set like MIPS. In this case, the EVM execution is decomposed into steps of MIPS instruction execution. An on-chain referee only needs to execute one MIPS instruction on-chain to decide whether Bob is Carl or Carl is lying. Since MIPS is a general VM, a vector commitment of the binary program file needs to be stored on-chain to ensure the referee is enforcing the correct EVM program. However, this scheme has several challenges. First, by committing the binary on-chain, the off-chain implementation is strongly coupled with the on-chain referee. Therefore, other implementations of EVM, like Reth or Basil, cannot be used to participate in the challenge protocol, since they will be compiled into different binaries. Then, the optimistic rollup is locked in with a specific implementation and has limited defense towards monoculture failure. Bugs in the Go Ethereum can bring down the entire network. One mitigation is to store multiple commitments of binary on-chain and require a quorum of implementation to be correct. However, this scheme is still not ideal. First, this is still a permission solution, requiring the governance to manage all the on-chain commitments. Second, during a challenge, interactive fraud-proof games must be run for all binaries, so it is not scalable and is complicated in real-world operation. To summarize, the compilation-based IFP scheme precludes permissionless and trustless inversion programmability. Furthermore, the trusted computing base of the compilation-based IFP includes both on-chain referee and off-chain implementation, even the compiler and the commitment generator. The complex and large TCB results in a large attack surface. Therefore, it is hard to audit and infeasible to formally verify the entire trusted computing base. Thirdly, every off-chain component modification will change the binary, even if it is only a performance improvement or vulnerability patch. Therefore, the on-chain commitment needs to be updated very frequently to reflect on off-chain changes. And since the only on-chain footprint of the upgrade is the replacement of the commitment, the upgrade process is less transparent. We propose a new approach called L2 native interactive fraud proof to solve those issues. We observe that we must decouple the protocol from the implementation. And to decouple them, the on-chain referee must natively target highest possible level of L2 semantics. In fact, we argue that this is a general principle when designing a remote delegation of computation protocol to enable permissionless inversion programmability and to reduce attack surface. And it is not just limited to the optimistic rollup case. In our system, Specular, we identified that although the clients are implemented in different ways using different languages, they need to implement the exact same EVM semantics. Therefore, we could add an abstraction layer of EVM semantics to decouple the on-chain referee from the off-chain implementation. In this case, the on-chain referee should emulate one EVM instruction on-chain. By introducing the abstraction layer, any EVM implementation can be used to participate in the challenge protocol permissionlessly. Therefore, Specular has permissionless and trustless inversion programmability. Furthermore, the trusted computing base only contains the on-chain referee itself. The off-chain implementations are no longer inside the TCB. So Specular has the minimal TCB. Therefore, it is easy to audit and even feasible to formally verify. Moreover, as long as the EVM semantics of implementation does not change, they could use the same abstraction layer to participate in the challenge. And no on-chain upgrade is needed for the off-chain upgrades, like for performance improvements or vulnerability patches. So our system has an infrequent and transparent upgrade process. To implement the one-step EVM emulator in the referee, we encapsulate EVM execution states into authenticated data structures. For example, we use hashchain for the stack and Merkle tree for the memory. Therefore, we only need to review necessary state on-chain to emulate one EVM instruction. We implemented the L2 native interactive fraud proof with minimal modifications on existing Ethereum implementations. To demonstrate the capability of inversion programming in our solution, our implementation supports both Go Ethereum and Aragon, which are the two most popular Ethereum implementations. We evaluated our IFP system on random transactions interacting with three popular dApps, namely Uniswap, Ethereum Name Services, and Ballot. The evaluation has shown practical performance of the dispute resolution. In summary, by adding an abstract semantics layer between on-chain referee and off-chain implementations, Specular is the first interactive bulletproof system that supports permissionless and trustless inversion programmability, has a minimal trusted computing base, has a transparent upgrade process, and has efficient dispute resolution protocol despite the intricacy of EVM. Here is my email and a link to the paper. Feel free to send me any questions you may have. Thank you.